Okay, gravitational force. So far in our discussions of gravitational force, I've just told you that there is just an attraction of a mass to the Earth, and the equation for that is just Fg is equal to mg. And so what we're going to look at is more bigger picture and really understanding where that equation comes from. So fundamentally, gravitational force is the idea that any object with mass, so any object with mass is attracted to any other object with mass. And it's one of the fundamental forces. So any two objects that have mass are going to have this force of attraction, this gravitational force of attraction there. So technically, I have mass and this marker has mass, and so there is a gravitational force of attraction between myself and this marker. It's so small and insignificant that it doesn't affect any part of my being or my life. And that's true. Whenever we see a gravitational force, unless one or both of your objects is really massive, we do not see the effects of gravitational force of attraction. And so that's why we primarily only see it with our Earth, because it's such a huge mass. Something to know about gravitational force is it is an action-reaction force. So it's an equal and opposite force. So again, with my example with the pen, I am exerting a force of attraction onto this marker, and the marker is exerting an equal and opposite force of attraction onto me. Again, we don't see it so small and significant, but if we looked at a little bit of a bigger scale, like the Earth and the Moon, we definitely see the effects. So the Earth has a gravitational force of attraction to the Moon, and we see that because the Moon is in orbit around the Earth. But the Moon has an equal and opposite force of attraction to the Earth. So if I were to look at kind of Earth and Moon, there is a force of gravitational attraction that way, and then there's a force of gravitational attraction that way, and those two forces are equal and opposite. The consequences are different because the masses are different. So when the Earth pulls on the Moon with this Fg, the Moon is stuck in orbit around the Earth. When the Moon pulls on the Earth with this Fg, the result is we see the effects of the tides. So there is definitely an effect in that case. It's just the effect isn't as drastic because of the drastic difference in masses. Okay? So let's actually look at the equation for gravitational force. So this is the general equation. This is the general equation for gravitational force anywhere in the universe. It's not just here on the Earth. And so our symbol, because this is the general equation for the force of gravity, is F sub big G. And then the equation for it is that F big G is equal to big G m1 m2 over r squared. So let's kind of talk about what these quantities are. M1 and M2 are just the masses of the objects that are attracted. R is the distance. I know R usually stands for radius, but R is the total distance between the two objects. And usually this is going to go from center of one object to center of another object. And then big G is called the universal gravitational constant. So it's a constant no matter where you are in the universe. It always is this given number. And this given number for big G is 6.67 times 10 to the negative 11. And the units are kind of funky because it just has to match whatever it is I need to have so that I have newtons on this end. So the units are Newton meters squared over kilograms squared. Okay. So that's this in this equation, that big G is always going to be 6.67 times 10 to the 11. So let's just look at an example of the gravitational force here on Earth. So a few things to kind of know for this example is just what the mass of the Earth is and what the radius of the Earth is. And I'm going to switch over to here, mix it up a little bit. So let's say, this is not to scale. Let's say that you have, here's the Earth, and here you are. Again, not to scale. And let's say you jump up. And so momentarily, you jump up, and your feet are in the air. And again, not to scale, let's say you're 1 meter off the ground. So if you're 1 meter off the ground, in terms of force diagrams, the only thing you have acting on you is F big G. Okay? And again, we're zooming out, not looking at what we've known so far with the idea of weight. You just have F big G. So if you were to think about forces, the only force you have is this F big G, and that should be equal to MA. That's what Newton's laws tell us. So let's actually go ahead and plug in some numbers. So I've got F big G is equal to big G M1. We'll call M1 the mass of U. And then M2 would be the mass of the Earth over R squared. And this is going to equal M1 times A. And the reason it's M1 is because we're looking at the force diagram on U. So you can see that there's an M1 on each side. And that will cancel. And so then we're left with big G, mass of the Earth over R squared is equal to your A. Big G, we have it's the constant, mass of the Earth we have here. Now radius, technically radius is from center of an object to center of an object. So from here to here is, oh, I should leave it as a little r, huh? Is your radius. So that radius, that r, will be the radius of the Earth plus the height that you have jumped off. But if you think about it, just kind of grand scheme of things, if the radius of the Earth is 6.37 times 10 to the 6 meters, is one extra little meter going to really count? Not going to make that much big of a difference. So for our purposes, our r is approximately equal to our radius of the Earth. So let's go ahead and plug in the numbers that we know. So for big G, I have 6.67 times 10 to the negative 11. My mass of my Earth I found right here is 5.98 times 10 to the 24. And then my radius is 6.37 times 10 to the 6 squared. So go ahead and calculate that out. And then the video will pause and you can input your answer. And you should have gotten that the acceleration was approximately 9.8 meters per second squared. So that's where that number comes from, how we can actually figure out what that gravity is. And so that makes sense then why when we do here on Earth, when we think about our FG, it just is equal to our mg there. Okay. So tomorrow in class we'll look at just some more examples of gravitational force on just different celestial bodies and just kind of conceptually look at that as well.